So we now continue with Paul Williams of the Natural History Museum of London. And he's taking Asian bumblebees as key to the European bumblebees. So Paul.
Thank you. Just trying to make sure that we can see the slides. Can we see that clearly? Is that good?
I will check. There's some time lag, so
I
think it's good.
Excellent. Thank you very much. Right. Okay, so I'm Paul Williams. I'm at the Natural History Museum in London, and I work on Asian bumblebees. So I've got one of your bars of instructions across the top of my slide, so I can't read it. That's helpful. Never mind. And so I was trying to think of something to say about, what we could learn about European bumblebees from looking at Asian bumblebees. I'm still trying to move. There we go. Got rid of it. Good. Can you see? I've got something about. Please move something away. Oh, that's it. Okay, so I'm back on track, I think. Right. So what can Asian bumblebees tell us to help our understanding of European bumblebees? And I've still got all sorts of bars of information across the top of my slide presentation.
Yeah, I see them also. So can you try to remove them? I'm not sure what
I would love to remove them, but I'm not sure how to do it. Anyway, so I was going to start with a picture of Bumblebee Diversity, which some of you may have seen before. This is a map of species richness and the numbers of species among equal area grid cells. And this has been compiled by looking at more than 30 years of collection of data by identifying specimens and plotting distributions of individual species. And what it shows us is that the largest numbers of species per unit area in these grid cells are in Asia, and particularly around the Qinghai Tibetan Plateau. And it just crossed my mind that this probably suggests that there is something that we can learn from Asian bumblebees. So my experience of Asian bumblebees really started in 1980 when I was working in Kashmir, Himalaya. And this is a picture on the left of the Great Himalaya, which is a very spectacular habitat for bumblebees, and lots of species, lots of high density of bumblebees. And if you go over the top of this mountain range, it rapidly becomes much drier. And although there are a few plants around here, there are actually no bumblebees. You have to go up quite high to around 5,000 meters, 4,000 or 5,000 meters to start to see small patches where there are bumblebees maintained by permanent summer streams coming out of glaciers that feed the plants that feed the bees. But these bumblebees are still very interesting, and they're very rich, and they're the ancestors of many of the things or they're closely related to the ancestors of many of the things that we're looking at in Europe. This is going much further east to the north of the Tibetan Plateau, to the Kunlun Mountains. Again, the patches are very few and far between, but where they do occur, they're full of very interesting things. Is there some way of getting rid of this bar? Vincent?
I must say that I have no idea what it is, and I have also no idea how to get rid of it. So right. I'm not sure. I think it's in your laptop, but
okay. I've never seen it before, so it's some of it's just disappeared. I don't know what that's all about. Okay, so going even further east on the plateau, it does eventually start to get wetter, and we see these amazing vistas of flowers stretching to the horizons, lots of wonderful things like pedicularis, and lots of species of bumblebee. If we get beyond the Qinghai Tibetan Plateau. There's a mountain range going across North China off towards Beijing and beyond. And the bumblebees here are restricted very much to the mountaintops. There are some in the valleys, but they're mostly in these little patches of relatively undisturbed habitat on the tops of the mountains. I've been very fortunate to be able to spend about 20 years looking at these bees all across about half of the provinces of China, thanks to working together with colleagues in China. And they send out people every year to all over China, bringing back thousands and thousands of bees. And my job was to try and make sense of this to identify these bumblebees and find out what we were looking at. So I was going to talk about three things briefly. Firstly, the fundamental question of how many species are there, what species are there? And this really simplifies down to telling the difference between polytypic, widespread variable species and complexes of local species, often cryptic, as we've been hearing before. And it won't come as a great surprise to many of you that the solution to this seems to involve looking at the variation in these bees across their entire range. So we need to have all of the species in the analyses, and we need to have all of the variation within these species in the analyses. Here's an example of one of those sorts of questions that's been raised in Europe. There's a group of bees called the Sicily Complex, and they come in lots of different color patterns, as shown here in Lecoq in 2015. And people have asked how many species are present. Well, to recognize species in practice, the consensus these days is on using an integrative approach. And this is an approach where you look at various lines of evidence for how many species you have, and then look for corroboration for where there's agreement in support of a particular solution. One of these lines of evidence that I'm going to concentrate on is using species coalescence in a fast evolving gene like a CO1 barcode to look for evidence of evolutionarily independent lineages. And this is particularly valuable because it's close to the theoretical concept of a species as independent evolutionary lineages, which is, gives it particularly good support. So if we have a series of sequences from samples that we've taken that represent what's extant, we can use techniques to reconstruct an estimate of the evolutionary relationships between these extant sequences. And we tend to see a pattern that simply, at its simplest, looks like this, that we have a lot of short branching within what are thought to be species, and then we have long branches between those species. And so we can turn this round and fit models to try and detect these species by looking for the short branching, using a model of short branching and a model of long branching, and see where we get the transition points to locate where these coalescents are likely to be, and hence where our species are. Looking at that in some real data for melanobombus, the Lapidarius relatives, but we're particularly interested in Sicily. This is the result of using all of these sequences for the CO1, and this is where the Sicily complex comes out. So here they are here. And with all of the sequences involved in the analysis, we find 8 candidate species. Unfortunately, the bad news is that this solution is very unstable to taking out individual sequences or putting new ones in. So the number of species tends to change rather erratically, and that's not a good thing. So we start to look at potential sequences of potential sources of bias in this. And the most obvious one is going to be to look at things like the pattern of sampling between areas and between taxa. And to try and reduce this bias, one way of doing it is to take out duplicate samples, duplicate sequences. And when you do this, when you use only the unique sequences, you get from the models, you get a tree that looks like this with a single species in it, single coalescent transition here. And this solution is very stable with respect to taking single sequences out or putting new ones in. So we've got a little bit more faith in that. If we look at the constant, can anybody, has AVL or anybody worked out a way to get rid of these things? Can you see these?
It's likely that there is another program or screen still on your laptop or PC. So I think the only way to get rid of it is stop sharing your screen and then close other windows and then share again.
Okay, let's try again. No, it's still there.
Then I'm afraid that we cannot solve it at the moment. So
okay, right.
I'm sorry.
Yeah, okay. That's interesting. It wasn't there when we did our practice run. Okay, so the consequence of this, if we look at where those samples that we use to build that tree are across Europe and Asia, these are the locations of those gene samples. And you can see that we've got lots of bees with yellow bands, bees with white bands, bees with red tails, bees with pink tails, bees with white tails, all sorts of variation. And all apparently, according to this genetic evidence, parts of one species. But this isn't the case with all of the groups in these trees. So if we look at the Cariensis complex, which is pretty much the sister group to Sicily, then initially with all of these sequences in, we identify 6 species from the coalescent analysis. And if we reduce it to the unique sequences, we still get 6 species. And these are very robust to adding or subtracting sequences, which is good news. There's another aspect of these data which is quite interesting in relation to whether or not these are one or more species. If we look at the relationship between the distance that two sequences were taken and the divergence between those sequences, within a single population of a single species, we expect there normally to be a positive relationship between these two things. And for the Sicily data, within each of the initial species, as you would expect, there is such a significant relationship. And there's also such a relationship among those or between those initial species. So those 6 initial species, those 8 initial species are behaving as though they're all parts of a single species. So this seems to provide some sort of additional support for this idea coming from the coalescent analysis that we have one species present. In contrast to this with the Cariensis case, where the coalescent analysis consistently said that there were 6 species present. Within those 6 species, we find the divergence with distance relationship, but it's not present between those 6 species. So that corroborates what we were seeing from the coalescent. For those 6 species projected into the geographical space, each species distribution is plotted in a different colored spot. These are just the samples that we use to generate the tree. Actually seen many, many thousands more of the bees in many, many other areas. And of these 6 species, 3 of them include both yellow-banded and white-banded individuals, showing how color varies within species yet again. Coming back to where it started on this and what this can tell us for Europe, there's an endemic Eastern European bumblebee here, Bombus allergesianus, which appears to be well supported as a true species and one which is quite separate from the Asian species, which they originally believed to be parts of the same species as Cariensis. So the support from this analysis shows that this is a genuine endemic. And secondly, we found a white banded color form of this thing that was not recognized before. So we know what limits of the species are, and we know what the variation is much better. And going back to our example of Sicily, we now have much better evidence that all of these different color patterns are parts of one species. The second point I wanted to talk about was, where do the European bumblebees come from? Where do the lineages come from? How do they get into Europe? So this is going to the question of how are species assemblages put together. And I'm going to focus very much on mountains as a corridor for dispersal from Asia into Europe, and particularly through southern Europe. This is staying with melanobombus again, just for a minute. If we look at the data we have from the analysis of melanobombus and run a biogeographic analysis, this supports a principal dispersal corridor through these mountains from Asia, through the Middle East, and into southern Europe, probably in a period about 8 to 4.5 million years ago. But we can look at this in a lot more detail by looking at the group Bendacu Bombers, because these are much more specialized in more extreme habitats right at the top of mountains. And if we look at the data here, we've got distributions of these bees in Asia, in the high mountains, and in Europe. But we have 3 big gaps, 1, 2, 3, in their distributions where they don't currently occur. I'm going to focus on this one, which is the route from Asia into Europe, and this is going through Afghanistan and Iran. And these mountains are currently too low, with too warm and dry a climate to support Bendacu bombers. And yet, if we look at the genetic evidence, it would appear that these bees should have, or most likely to have, spread from Asia into Europe between about 8 and 3 million years ago. So how is this possible? Well, what we can do is we can try and look at the evolution of the climatic niches of these species through time. And you simply plot the climatic niches of the extant species and model them back along the tree to see what the climatic niches of the ancestral species are likely to have been. At the same time, we can look at modeling past climates, and what I have here is 3 time slices, one at 3 million years, one at 8 million years, and one at 15 million years. And by combining the climatic niche of the bees with the changing climates, we can map the expected suitability of different areas at different times in the past. And what we see if we use the current niche of these bees is that this gap persists in these models. It doesn't look like a very favorable route through from Asia to Europe. But when we combine the past climates with the models of past climatic niches, we get a clear winner around 8 million years ago, when there seems to have been a relatively high suitability in these mountains in Afghanistan and Iran for these bees to have used this as a corridor to get through into Europe. So what we're doing here is putting together the information on the orogeny, the uplift of the mountain chains, from the genes to say when these bees are likely to have moved between different places, to look at the ancestral climatic niches of those bumblebees at that time, and to look at the changing climates, and to identify from that the most likely scenarios for these things to have used these corridors to get from Asia into Europe. And they do fit in this case. I'm looking at that in a number of different groups of bumblebees at the moment. But you can see here, even in the richness map of bumblebees, current richness map across Asia and Europe, there's some sort of signature possibly of this corridor of spread from Asia into Europe in this ridge of high pressure through these, ridge of high richness through these southern mountain ranges. But it may be that some of the long-term surface nesting grassland bees actually came more recently through these northern grasslands, and that's another pattern that I don't have time to talk about. Just lastly, very quickly, a few comments on conservation and the need for priorities both in Europe and globally. A high-profile example in Britain, which no doubt we'll hear about, is Bombus subterraneus, which was extirpated in Britain, and we can see it here from the NBN data, after 1988. This is a photograph of one of the last British subterraneous I saw in 1982. But this is a very widespread species that goes from southern England all the way through to the far east of Asia in various different color patterns. And in some of those areas in Central and Eastern Asia, these things are still relatively common. So here's a meadow in Inner Mongolia, and this is a Bombus subterraneus from one of those that was happily flying around there. An even more extreme case is Bombus calamanus, which was extirpated in Britain after 1941. Its last known site is the grasslands around Seaford on the south coast. But it turns out from the genes that this is likely to be part of a very widespread species that includes various yellow and white banded bees from Central Asia and Mongolia. And these things are very widespread. And in some of their areas of distribution, like here in the Siberian steppe, Alexander Bivaltsev has found these bees to be the second most abundant bumblebees in quite a number of locations. So they're doing very well in some other parts of their range and not uniformly threatened. And this is really the point that I wanted to make, that there are other species like Bombus alpinus, which is vulnerable in Europe, but Europe is really its only place of occurrence. So where these regional and global priorities, which are both in themselves valid, where they coincide, we have species and areas that are especially important for conservation. And that's the point I wanted to make there. So thank you to all of those who have helped in the collection of these data through supporting collecting trips, collecting specimens, giving access to collections, obtaining sequences and funding travel. And I'll leave it there.
Thank you. Impressive talk with lots of information. There are several questions. So one question is by Doc Sponsler. And he's asking, do you have any evolutionary hypotheses to explain, well, now it's shifting for me, why color pattern is so liable within bumblebee species?
Right. I had a look at bumblebee color patterns worldwide a while back, and we can find several, we know of, various explanations for why these things may have advantages. That may not be quite what you're asking. You might be asking more, how do these differences arise? And obviously, there's mutations going on because these things are heritable. I can't really speak to that in any great detail because it's not my subject area. But the advantages of the color patterns, there seem to be several. The one that everybody has always focused on is Müllerian mimicry, that bumblebees sting, and that therefore there's an advantage to the bumblebees of different species to have similar color patterns in the same area. And there's very strong statistical support that those convergences are actually what we see. So we see yellow-banded bees in Southern Europe and white-banded bees in Asia, and bees with red color patterns in the old world and no much less red in the east of the new world, for example. There are questions about crypsis. This is something that's not been looked at nearly so much, but if you've ever looked at bumblebees foraging in late summer in drying grasslands, then the ones which are more or less uniformly yellow or brown are often much more difficult to see flying against drying grasses, and maybe that's important for protecting them. People have talked a lot about thermoregulation, and they think, oh, black bumblebees, they must be occurring in the far north where they can absorb more energy and warm up more quickly. But in fact, black color patterns are pretty much restricted or most frequent in the tropics, lowland tropics. And I can talk at length about this, but we see that at the lower elevations in the Himalaya, the bumblebees tend towards black thorax initially and being black all over in the more extreme cases. And this seems to be related to heat stress when they're flying around in the sun. They tend to avoid flying in the sun after the early morning. So there's all sorts of things going on, and there's lots of opportunities for people to investigate this in a lot more detail, but it's difficult because the hair is thick and there's a lot of complicated physics in there, I'm told. Anyway, long rambling answer.
Yeah, long answer, and basically it's not really known. I think that's the answer. Or
lots of ideas, not very many good tests.
Okay, I've one short question left. So your presentation gave the impression that most of the diversity in Europe has arrived from Asia, but is that true, or did also European species move into Asia?
Undoubtedly, things have gone in both directions, but I can't quantify that at the moment. What we can see is that bumblebees, centers of origin is a very dangerous concept, but it does look like bumblebees, early bumblebees started in Asia, and that we acquired them from Asia.
Okay, thank you. Okay, thank you for this presentation. We have to move on to our third presentation. So thank you, Paul.